Welcome to lecture 31. We started a new module on stability of slopes. You would also read in the papers that a lot of landslides take place in the mountainous area. The reason why landslides take place is the slopes are unstable. They may be stable at some stage, but because of rainfall, melt, or road cutting, etc., they become unstable. We said that there are two kinds of material. You can have rock slopes, where the material is predominantly rock, jointed rock, etc. We will not be discussing that, but we will be talking of soil slopes, where the material of the slope is made out of soil. We basically try to express the stability in terms of what is called as factor of safety. It gives you the margin of how safe it is. We say that we can define in terms of three different alternatives: strength available divided by the shear stress mobilized. So this, if I say tau available and tau mobilized due to whatever actions of the gravity, stress, etc. We can also define in terms of force resisting sliding divided by force causing sliding. Third one would be in terms of, suppose I say this is F required, F available divided by F mobilized or causing failure. Third one would be in terms of moments of forces resisting, say, slope instability divided by moments of forces causing slope instability. So I can say MR is the moment resisting and moment activating is M activating. Ratio of these gives the factor of safety. To be a good designer, all the factors of safety generally should be preferably more than 1.5. In short term, suppose you want for a very short period of time, you may accept a slightly smaller value of 1.3. But when you design, generally it's good to design for a larger factor safety of 1.5. And the way we do this analysis is very simple statics. Like we discussed in the last class, looking at a block, we find out the ratio of force mobilized by force causing sliding of a box or a block on a flat table. Now let's take first an infinite slope with some rock surface. Suppose I have, this is the slope consisting of soil here, inclination is beta, and this is rock. This you find in many mountainous regions, that the top cover is soil and that may be of finite thickness. If I call this thickness H can be, let us say, 1 to maybe about 5 meters. So what should be the likelihood of this soil sliding along this surface? In order to do this, first let me define this as infinite slope. We would like to take a small slice. Let's say the width of the slice is L, this thickness is H. The material has unit weight gamma, C cohesion, and phi angle of shearing resistance. Let us try to draw the free body diagram of this block A, B, C, D. Let us say I am looking at A, B, C, D. So the forces acting would be W. Simple. W is the weight of the soil block ABCD. These are the forces that from the upstream soil is trying to push it, and the soil below on the left is trying to resist, and we assume them to be same because of symmetry, and then because the whole thing is contained in this. So what we need to do is this force W able to cause sliding or not? Now if I look at this force and resolve it along, this is beta. So what is the normal component and the tangential component? So can I say normal and tangential? Similarly, this reaction from the ground I can say is normal, and now I would like to say what will be the shear resistance mobilized. What are the forces? W is the weight acting downward. Fr and Fl are the forces on the side, and because of the symmetry, it's an infinite slope, so the forces will be on either face equal and very similar, so we don't need to consider them. This block of soil is resting on the plane BC, and so the reaction will be equal to the weight W, but you can resolve both W and reaction normal to the surface and parallel to the surface. If I resolve W onto the normal, I get N, force N. If I resolve W along the parallel to the surface, it will be T. This angle being beta. So you can easily, from your first year, second year mechanics, you can say that N is equal to W cos beta. You can see that the angle between the horizontal and the bottom of the slope is beta. So the angle between the vertical and the normal will also be equal to beta. So when I resolve the force W here along the normal, the angle is beta, so it becomes W cos beta. Whereas the tangential force T will be equal to W sin beta. Okay. Now, what will be W? Can I say W is equal to gamma unit weight into volume? Unit weight into volume will give me the weight of the element. And can I say this is equal to gamma area ABCD into unit distance? These slopes, we assume they are very long, infinitely long. All these problems are usually called plane strain problem. What it means is whatever strains, stresses, forces, they can be only within the plane perpendicular to the board. We are not interested in the deformations because the same soil is existing for maybe hundreds of meters on either side. So if I take a unit length perpendicular to the board, that will give me multiplied by area volume. What is ABCD? For a simple quadrilateral or parallelogram, you can say it's equal to L times H. So this will be equal to gamma L into H. Of course, 1 is understood as far as W is concerned. So now you can say that the forces are known. We need to calculate the stresses now. So this force normal, N is equal to gamma LH into cos beta, and the shear force T is equal to, maybe let's write it here, gamma L into H cos beta. This is gamma LH into sin beta. So these are the two. Now let's look at the area of the plane BC, because this force, normal force, is acting on this plane BC. So normal stress sigma is equal to normal force by area, which is equal to N by BC into 1. I am looking at length BC into perpendicular distance 1. Now if L is the horizontal distance, what will be BC? From simple trigonometry, BC is equal to L secant theta, secant beta, or shall I say L by cos beta. BC, the length is along the horizontal we showed earlier, and the angle is beta. So when I want to find out length BC, it will be equal to L secant beta, or I can say L by cos beta. Now if I want sigma, it is equal to N is equal to gamma LH cos beta divided by L by cos beta. Cancel L, you will get gamma H cos square beta. So the normal stress on the plane BC is equal to unit weight gamma times the height or thickness of the soil layer above the rock surface, or whatever interface you have there, multiplied by cos square beta. Similarly, if you want to calculate the shear stress tau, it's equal to T by area, which is equal to gamma HL sine beta divided by L divided by cos beta. Again cancelling L, can we write the shear stress causing sliding? Tau activating sliding is equal to gamma H sine beta into cos. You simply have divided the force by the area BC. Please remember, T is parallel to the surface and BC is the plane. So force by area gives me the stress. And since this is parallel to the surface, it's a shear stress. Whereas N is normal, so we call it normal stress. So we have sigma and tau. Now on the reaction from the stable mass here, because we are saying this is trying to move down. So when you look at it, when I look at the force W, the normal force and the shear force is downward. So this T causes instability. What will be the resistance mobilized? For that, you go back to our Mohr-Coulomb criterion. Let me write here. Sigma is equal to gamma H cos square B. Now you say that strength of the soil at the base is C plus sigma tan phi. So what will that be equal to? C plus sigma is equal to gamma H cos square beta into tan phi. There are two ways of writing the same. Let me define the factor of safety, which is equal to tau. This is the strength. So this is equal to tau strength divided by tau activating, and that will be equal to C plus gamma H cos square beta tan phi divided by gamma H sine beta cos. This should be, the numerator tells me what is the strength that can be mobilized by the soil along BC because of the strength parameters C and phi, and the normal stress is sigma. Whereas the denominator is the shear stress caused by gravity, and this ratio gives me the factor of safety. If C is equal to 0, that means soil has no cohesion, it's only a frictional material. What happens? If C is 0, this gets cancelled. Let's write the factor of safety now in a simple form. If C is 0, can I write it as gamma H cos square beta into tan phi divided by gamma H cos beta into sine beta. A very simple expression. You can simplify further, saying that gamma H is in the numerator and the denominator, you cancel it. There is 1 cos beta, you cancel it. You will get tan phi divided by, you have cos beta multiplied and sine beta. We can write it as tan phi in the denominator, you write it as tan. Very simple expression. So the factor of safety is equal to angle of shearing resistance tan phi divided by tan of the slope angle. Now, which means suppose I have a granular material with phi is equal to something like say 32 degrees. Then tan phi, tan 32 is maybe around approximately 0.6. And tan beta, if it is let us say a 2:1, the slope angle is 2 horizontal is to 1 vertical, which means tan beta is equal to half, that's 0.5. Then the factor of safety will be equal to 0.6 by 0.5, which gives me 1.2, which is safe but not a good design. You may have to make it probably flatter than 2:1. We normally say maybe it's good to have 2.25 h is to 1 vertical or 2.5 h is to 1 vertical. If you do that, the slope will be very stable for all conditions that you can think of. So for a granular material, it becomes very easy to analyze the whole problem. Let us see what happens when phi is 0 and you have only C. Then you can also find out very easily that it will be C by gamma h, and you can have fairly large value factor of safety. If phi is 0, then what happens? This term becomes 0 is equal to C by gamma h sine beta into cos beta. Very simple expression. It doesn't, of course, phi doesn't come into picture. You can also write it in a slightly different way. What will be h, which is equal to C by Fs into gamma sine beta cos beta. So I know this will be the critical height or the height corresponding to given factor of safety. If factor of safety is equal to 1, h is equal to C by gamma sine beta cos beta. So we can work it out. We sometimes use a symbol C by gamma h as a stability number. We'll come back to this. This is what Taylor has given at some stage. This ratio, C is in terms of stress, cohesion, is kilopascals. Gamma is unit weight, kilonewtons per meter cube, into height gives me again stress. So this becomes a non-dimensional parameter. So n is called stability number. We'll come back to that later when we study Taylor's charts. So you can work out the stability of infinite slopes. Now suppose the slope is saturated and there is some flow. What happens? We have infinite slope with seepage, which means when you are looking at this, the flow is taking place, the soil is saturated, so gamma saturated gives me the saturated unit weight, and gamma buoyant or gamma submerged will give me gamma saturated minus gamma W will give me the buoyant unit weight or the effective unit weight you can think of. If I do that, again we go back to our forces. Here I would like you to realize one thing. When I look at the weight, I need to look into the total weight, weight of the soil and weight of water, so I will take gamma saturated. But when I'm looking at strength, and if you remember, we said that tau is equal to C plus, because now it is saturated, I would like you to consider only effective stresses. Why? Because water does not have any shear resistance. So when I calculate the total stress, I have to subtract the port pressure. So I would write it as C plus sigma minus U tan phi. And in order to represent, I'm talking of only effective stresses. We'll talk of only the drain parameters C prime and phi prime. Please remember, pore pressure does not cause, does not mobilize any resistance because water has no shear resistance. And when we looked at the effective stress principle in module 3 or 4, we said that sigma prime is equal to sigma minus u, and only the effective stresses control the soil behavior. So when I calculate the reaction from the total normal stress, we'll have to subtract the pore pressure. Now if I look at the pore pressure, you agree that this is the flow line. Flow lines will have to be parallel to the surface. Water will flow along the surface. So what will be the equipotential line? It has to be perpendicular. This angle will be 90 degrees. The flow line is along beta, the slope. So we have to find out what will be the equipotential line. We know that equipotential lines and flow lines are orthogonal to each other, so we say it is perpendicular. So whatever pore pressure if I want, it will be equal to this length, let us say L prime. That will be the height of water. Sorry, I need to find out the height of the water. So if I put a piezometer from here, the water level will come up to here. So what is the normal distance here? If I can do that, this is h, this is beta. So this will be equal to h cos beta. So please remember, the pore pressure is equal to h cos beta. Because what is the equipotential line? It has to be perpendicular to the flow line, and if I draw that, it will go up to the top of the slope. And if I put the piezometer, the water level will rise up to the top of the slope. It cannot go beyond because then it will flow outside the soil. If that is so, the height h is equal to, this distance, what shall we say, small h is equal to h cos beta. So now we'll write the strength mobilized like before. Tau is equal to C plus sigma minus u tan phi is equal to C plus, we said sigma is equal to gamma h cos square beta minus this height, so this is gamma w into h cos beta, the whole thing multiplied by tan phi is the strength mobilized. This is the normal stress and this is equal to the pore pressure. Okay, I think we get another cos square beta here because I have to consider the length here. So if I now want to calculate the factor of safety, it will be equal to C plus, I can say gamma h, gamma saturated here, gamma w into h, that gives me gamma prime h cos square beta into tan phi divided by the shear stress mobilized, which is equal to gamma saturated sin beta into cos beta. Please remember, here we are talking of gamma prime is submerged unit weight, gamma saturated minus gamma w. I taken the cos squared because the length here of the slice BC is again h by cos beta. So we take care of that, and if I now look at it very simply, what you will get is C plus gamma h, gamma prime h cos square beta tan phi by gamma saturated now. In the numerator, because I am looking at effective stresses, I am looking at the submerged unit weight or the buoyant unit weight. But the force that is causing sliding is the total unit weight. So now if I can simplify this one, for C is equal to 0, we will get gamma prime h cos square beta tan phi by gamma h sin beta cos beta. Cancel again. This I'll say gamma saturated, cos beta cancels. So you will write this factor of safety is equal to gamma prime by gamma saturated into tan phi prime by tan beta. You get one of the most simple, elegant solutions which will tell you what happens if the same slope got saturated and there is a flow along the slope. Earlier we said if it is a dry slope, unit weights are same and we cancel them, you will get tan phi by tan beta. If it is saturated, you will find that gamma submerged by gamma saturated into tan phi by tan beta. If I take gamma saturated as something like maybe say 19 kilonewtons per meter cube, gamma saturated is 19 kilonewton per meter cube, whereas gamma prime is equal to gamma saturated minus gamma W, which is 19 minus 9.8, so that gives me around 9.2 kilonewtons per meter cube. So if I want to take the ratio gamma prime by gamma saturated, 9.2 by 19.8, I'm sorry 19, let's say approximately 0.5. So the factor of safety now is about half of what it was before. The most unique, very simple relation you get, the factor of safety reduces by about half the moment the soil gets saturated. So now you know why when it rains you find so many failures taking place, for the simple reason the factor of safety reduces. Suppose you have designed your factor of safety as 1.5 for the dry condition. For the wet condition, it becomes half of that for a purely granular material. It will be somewhat more in case of cohesive soils because we have the cohesion term too there. So we don't need to worry in case of cohesive soils. If there is C, there is no problem. So with seepage, factor of safety is equal to C plus gamma prime H, what is that, cos square beta tan phi by gamma H, gamma saturated here, cos beta sin beta. So I can say this is equal to C by gamma S into H cos beta sin beta plus gamma prime by gamma saturated tan phi by tan beta. So if the soil has cohesion, the slope is likely to be stable. If there is no cohesion, the chances are it may fail. So please note that this is how you can easily figure it out what will be the factor of safety in case of slopes with seepage or slope saturated ones. Now let's look at finite slopes. Finite slope means we are looking at a given height h from the top to the bottom, and of course the properties here are C, phi and gamma, and the slope angle, as we said earlier, is beta. What kind of things can happen? Let's look at the possible failures, modes, or shall we say mechanisms. First, it can fail along a line, plane here, AB. So that could be a sliding failure along a plane. 2, you can have a circular arc of failure passing the toe. This is the center O with radius R. So you can say there's an arc of a circle and the soil here will try to rotate. So sliding through an arc of circle and the failure surface passes through the toe. So we call it as toe failure. What is toe failure? The failure surface daylights on the toe. You can have a base failure, which is if I have soil here is somewhat softer, I may get a failure surface something like here. Again, this is circular arc, failure surface, and failure surface goes below the lower ground level. That is, this is the base. So within the base you will find it. Occasionally you find some local failures which instead of plane you may have simply a slope failure, shall we say shallow. It doesn't go up to the toe, you get it. The more general one will be, we have been all the time looking at circular failure surfaces, but now we also look at non-circular failure surfaces too. That's a more general one. Sometimes we also look at what is called as block failure, particularly in case of embankment. We'll come back to that later when we study embankments on soft ground. In that case, the block will be moving, being pushed by soil on one side and resisted by the soil on the other side. So let's look at this in the next class, various failure modes and how to calculate the factor of safety. Welcome to lecture 32. Let's study the stability of finite slope. This finite means finite height. The height of the slope is finite. It's not infinite like the one we considered earlier. So let us look at a slope of height h. H can be 5 meters, 10, 12, 15, etc. It can't be 100, 200. It's less than maybe about 20, 30 meters. And the slope angle is beta, as we said earlier. The properties of the slope are unit weight gamma, cohesion C, and friction angle or angle of shear resistance phi. One of the simple methods which was proposed long time back by one Mr. Kalman, we'll discuss this to illustrate the mechanics and the method of calculating. We do not expect failure to be planar, particularly in soils. Planar surface is not possible. Very unlikely, but it illustrates how the method can be used to calculate. So what I would like to take is passing through the toe at an angle. This angle is beta, this angle is theta. So if I say A, B, C, say this is D, let us say this will be a trial failure surface. We do not know where the failure is likely to occur, so let us say it is inclined at an angle theta with respect to the horizontal. So again, coming back to our earlier analysis, I need to know what is the gravitational force, then what is the reaction, normal force, and what is the shear strength that can be mobilized. As usual, we can always resolve this gravity into normal and the shear stress which is causing sliding along AC. So basically we want to calculate W. W, weight of the sliding mass, is equal to gamma into area ABC into 1, which is the thickness of the sliced perpendicular board. How do I calculate this? The triangle ABC, I need to get the area. So height I know is equal to h. I need to find out the length AB. I can find out as AD minus BD. AB length is equal to AD minus BD. And how do I find out? AC is the diagonal and h is the height. So can I find out AD in terms of, if this angle is theta, this is theta, so h by AD gives me tan theta. H is the so AD, h by AD is equal to tan theta, or AD is equal to h cot theta. Whereas BD, this angle is beta. Please remember, this angle is beta. So this angle is beta. So BD will be equal to h cot, sorry, this should be cot theta, and this will be cot beta. So this will be equal to h cot theta minus cot beta. So now we know the distance AB and we know the height h. So the area is equal to W is equal to gamma h into h cot beta. So cot theta minus cot beta. We know the weight W. So the normal component, like what we did earlier, I can get, which is equal to normal force is W cos theta. Again, please remember the angle between these two is theta. That we are looking at vertical, and this surface which is inclined at an angle theta. And the shear force, which is downward, T, is equal to W sine theta. So I can calculate the normal stress, which will be equal to normal force is W cos theta is equal to gamma h square into cot theta minus cot beta into cos theta. And the shear force T is equal to W sine theta. So it's gamma h square cot theta minus cot beta into sine theta. And if you want to find out the stresses, I have to divide by this length AC times unit weight, which I mean unit distance. So we need to find out what is the length AC. AC would be equal to, please note again, this angle is theta, and you want to find out AC, and this is h. So it will be equal to cosecant theta. AC will be equal to h by sine theta, or shall we say h cosecant. And so if I want normal stress, sigma is equal to normal force by area, which is equal to AC into 1. So that is gamma h square cot theta minus cot beta into cos theta by h. I take the sine theta above. And the shear stress tau, which is acting downward, is T by AC into 1. So it is gamma h square cot theta minus cot beta sine theta by h and another sine theta here. So that makes it slightly simpler. We can write now. So sigma would be equal to cancelling gamma h into cot theta minus cot beta sine theta cos theta, whereas the shear stress is equal to gamma h cot theta minus cot beta sine square theta. What will be the strength mobilized along AC? Tau mobilized is equal to C plus sigma tan phi. So C plus sigma we write from here gamma h cot theta minus cot beta sine theta cos theta into tan phi. Simply substitute with the tan of the angular shearing resistance, you will get the mobilized. So now you can say what will be the factor of safety for a possible planar failure surface. Factor of safety is equal to C plus gamma h cot theta minus cot beta sine theta cos theta tan phi divided by gamma h cot theta minus cot beta into sine square theta. Now this is for a given angle, planar surface inclined at theta. We want to find out what is the minimum factor of safety. We need to find what is minimum factor of safety. So when I look at this factor of safety, it is a function of C, gamma, phi, h, and of course theta. What are the terms? Plus of course beta, function of cohesion, unit weight, height of the slope angle, plus the failure plane theta. We do not know what is that plane which gives me the minimum. So when you go back to your basic calculus, in order to find out minimum, all that you have to do is take the derivative and equate to 0. So if I now differentiate d factor of safety by d theta and equate to 0, you will get the theta critical. What is that critical? Angle which will give you failure surface. And you will find that theta critical is equal to beta plus phi by 2. That's as simple as that for particularly the very little friction angle, etc. So you find that as you increase theta, when theta is 0, infinite factor safety because there is no sliding force. Theta is equal to 0, no sliding, because the plane is horizontal, so there is no soil which is pushing. When theta is equal to beta, no soil. If I increase theta, equate to beta, there is no soil at all, so no failure. So halfway between these two, you will get the factor of safety. And from here, you can go back and substitute. You will get a very simple expression for the factor of safety. And for factor of safety 1, suppose I say if factor of safety is equal to 1, that means the numerator and denominator are equal, and I can solve for the critical height, which we do. H critical is equal to 4c by gamma into sine beta cos phi prime by 1 minus cos beta minus phi prime. We get a very simple expression for the critical height. What I'm saying is, we try to solve this equation for the minimum, and the factor of safety is equal to 1, and in that case we get this expression. And you can see here the critical height, the maximum. If I increase the height more than this, it's going to fail. So I can actually find out the factor of safety is equal to H critical by H actual. This is where you can do that, which means I find out the maximum possible for a given beta, given friction angle, given cohesion and unit weight. So all the soil properties are given, and you can calculate the critical height, and the factor of safety is the critical height by actual height. And one simple particular case would be if phi is equal to 0. That means purely cohesive soil. Then if phi is 0, cos phi is equal to 1, and this will be, that's equal to H critical is 4c by gamma sine beta by 1 minus cos beta. And if beta is equal to pi by 2, what does it mean? When beta is pi by 2, we are looking at this angle beta, slope angle. It's a vertical cut. What happens? H critical is simply equal to 4c by gamma. So this is how we design these deep excavations for multi-storied buildings. If I know the c value, it will be equal to 4 times c by gamma. Let us say c is equal to some 30 kPa. So the maximum height of vertical cut, H critical is 4C by gamma. So when you are making an excavation, for example, in Visakhapatnam, Guntur, Vijayawada, etc., where you may get cohesive soils, you can tell the client how much is the maximum height and he can go without supporting the vertical cut. In Hyderabad, we have no problem because C is very high. Let us say C is equal to some 30 kPa. Gamma usually is of the order of 18 kilonewtons a meter cube. So if I now calculate what will be the H critical when I want to make a deep cut, it will be equal to H critical is 4 into 30 by 18. So this gives me 2, 9, 10, 3. So 20 by 3, about 6.7 meters. With a cohesion of 30 kPa and unit weight of 18, you can have maximum vertical cut of 6.7 meters with a factor of safety of 1. But if you want to have a factor of safety of 1.5, actual H would be equal to 6.7 by factor of safety. That gives me somewhere around 4.3 or 4.56 maybe. So that will be the maximum height you should allow for the construction of the basement. That may be. Whereas in Hyderabad, you can get C of the order of even 100 kPa, which means you have no problem. Most of the time, the cuts can be very deep, provided there is no water. You know, we have derived in the last class that if it's saturated, the strength reduces and the factor of safety becomes very small. So in case of dry condition, safe, but if it is saturated, may become unsafe. That is why you find during rainy season, lot of failures taking place. So this illustrates how we can calculate the factor of safety by postulating a failure surface and finding out the minimum. So the method of slope stability analysis, first you should know the geometry of the slope. Usually it is a planar one, but there may be situations where you may provide a bench or a berm, as we call it. So basically you need to know then you also need to know the height. The second would be the properties, geotechnical, C, phi and gamma. They may be constant or they can be varying. Suppose I have a slope, I may have C1, phi1, gamma 1, C2, phi2, gamma 2, and maybe below here I can have C3, phi3, gamma 3. So you need to find out how the soil properties can vary. The simplest, of course, when all of them are the same. Then we call them as homogeneous slope. C1 is equal to C2 is equal to C3. Phi1 is equal to Phi2 is equal to Phi3. The next step would be assume a failure surface. And we'll only consider circular arc from now onwards and calculate the factor of safety. And the next step would be search for minimum factor, which means you have to go back continuously. It's a iterative process. You assume a different failure surface, calculate factor of safety till you get the minimum. This is how we calculate the minimum factor of safety for slopes. Let me illustrate one of the simplest ways you can do, or the simplest problem. Let's look at a clay slope cohesive soil. So we have the height h, this angle is beta. Let me take a typical failure surface passing through the toe, and the center is at O and the radius is R. A, B, C. So ABC is an area enclosed by arc AC and the planes AB and AC. Okay. So what are the things that we need to do? Here again, now we are assuming this soil is moving along the arc. So we call this as rotational failure. Earlier, Kalman's method, where we had a planar surface, we have sliding. Now with an arc of a circle, what we are saying is the mass of soil contained in ABC is going to slide. So how do I find out? First, I find out the centroid. Say this is some point E and the weight W is acting here. Now you find out what is the distance, horizontal distance from the center. That is called X bar. Now you can see W, the weight, into X bar gives me a moment of causing sliding. So moment of forces causing failure is equal to W into X bar, which is counterclockwise, anti-clockwise. When this mass is trying to rotate to the right, you will see that the soil below is trying to mobilize resistance. And that resistance is, suppose this is a purely coarse soil, we said here, in an undrained state, because the failure may be very sudden, can I say it's equal to undrained strength is Cu. And if I now look at a small segment here, the force mobilized is equal to, say I'm looking at small delta theta, arc along, let us say, Mn, subtended by delta theta, arc Mn is equal to R delta. And the force mobilized along Mn is equal to Cu into arc length, which is R delta theta. And what will be the moment of this force with respect to the center? Moment due to force along Mn is equal to Cu R delta theta. And what is the lever arm? Is equal to R. The center is here, and this force is along the arc. And if this is the radius, you again agree that the tangent is perpendicular to it. So the force is tangential to the arc, so the lever arm is equal to R itself. What will be the total force? I have to integrate from A to C, and if this angle is, let us say, some theta naught, can I say that arc length is equal to R into theta naught, and all the forces will have the same lever arm. So the total moment, resisting moment, or moment of resisting forces, Mr is equal to Cu R square into theta naught. What we have done is basically integrated delta theta from 0 to theta naught. I can say that this came from that same equation, Cr square, Cu square, 0 to theta naught of delta theta. So when you integrate delta theta, it becomes theta. From limit 0 to theta naught gives me theta naught. So here is the total moment. So when this mass of soil is trying to slide down, what you find is the soil is mobilizing undrained shear strength along the arc length. So Cu into R into arc length is R into theta naught. This is theta naught. R is the arc length. So R into theta naught gives me the arc length AC into Cu gives us the total force, and each force, if I take the element, has a lever arm of R. So I get this. Now you can say factor of safety is equal to Mr by M active, activating failure. So that is equal to Cu R square theta naught by W into X bar. So this is for a given center and radius R. You may say, why should I take only one point? Can I take another arc? I can take a third one, etc. In this region, I can take a number of points, get the factor of safety. So I search in this space for different centers. So if I have a slope, something like this, and I expect the centers to be in this region, I take different centers and different radii and get factors of safety. Then we do contouring. You know how to do contouring? When you had in surveying different levels, we do how to find out the contours of corresponding to each height. Similarly, we have factor of safety of, let us say this is 2, this is 1.8, 1.6, maybe 1.41. Then you say the least value is 1.41, so the factor of safety for this slope is the minimum, equal to 1.41, whatever is the value. So this is how we do this. The only catch here is how do I calculate W. Rest of it is what you have seen. If I know the weight and the centroid with respect to the center O. We have located the center. You need to know so that I need to know the distance x bar. In the good old days, when we didn't have computers, etc., people were trying to find out from simple geometry this area and the location. So if I now look at the arc here, let's draw the toe failure. We don't want to make it more complicated. A, B, C, and this is equal to theta naught. Area ABC is equal to area of the sector OAC. First calculate this whole area minus area of the triangle OAB and area of the triangle OBC. This is OBC. Then you will get the area of the sector. Once you know the area, multiply by thickness, you get the volume, and multiply by gamma, you get the weight. Again, you know the centroid of the arc, you know the centroid of these triangles and sectors, and you can get the centroid of the sector. So it has to be done either graphically or with some amount of trigonometry. You can easily find out. It's a very tedious process. But when there were no computers and we only had to use either log tables or slide rule, this is how people were doing it. Of late, we have been able to, or they found a simpler version of the same, to do what is called as method of slices, which was given way back in 1920s, and now we have refined the same, given by a Swedish geotechnical engineer called Felinius. We go through exactly the same. This is theta naught. The height of the slope is equal to h. The soil properties are gamma, c, and phi. This is the trial arc. Center is here, and the radius is r. So given the center, we draw a line to the toe. This is called the toe of the slope. What he said was, divide this failure zone into number of slices of equal width. Let us say this width is b, or small b, let us say. And by plotting on a graph paper, I can find out the area of each slice if I know the height hi. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of slices usually is somewhere between 10 to 15. So what we do is we take a piece of graph paper, we draw the slope to natural scale, draw the trial arc, and this zone of soil which is likely to fail, slide or rotate about the center along this line, which is A, B, C. So it will slide along a C. Okay, so if I divide this, for example, you know this total distance, this is equal to B, and we have 12. So small b will be equal to B is equal to total width by number of slices. In this case it is 12, so small b is equal to the width of the failure surface by n, which is 12 in this case. Then I can measure these distances or the vertical height. So area of each slice is equal to AI is HI into B. So then you can calculate delta WI is equal to gamma into HI into B into, of course, 1, because 1 is perpendicular to the board, the thickness of the layer. Then we also find out what will be the angle with respect to the center, and I try to measure this angle with respect to the vertical, theta I, angle to the center of the base of the slice, so that I can now take the component of W along the base. Okay, so what is theta I? Suppose this will be fourth slice, this will be theta 4. So let me again draw it a little more clearly. This is the fourth slice, this is the center, vertical. So you draw this line, this gives me theta 4. This is the fourth slice, so I say what will be the angle subtended with respect to the vertical to the center of the base. Okay, so if I now take it, this tangent arc of a circle will be perpendicular to it, so that if this is B, you can say that the base width is equal to of the slice, suppose I call that as Li, B into secant theta I. This angle is theta I, so this angle also would be theta I. Vertical and the normal, horizontal and the tangent will be exactly the same. So I know the base width. You also know on each slice the force is vertical. If the number of slices is large enough, I can replace arc of a circle with the tangent, so each of them becomes a plane. So this is B, this is WI, so this is WNI, this angle is theta I. So you can easily resolve and analyze as before, and all that you have to do, and then since I know WI, I know XI, which means what is the distance from O, XI. I can find out the vertical component and very easily find out the contribution of the moment from these slices. So that is how we can do that, Li. So if I want the total moment of forces causing sliding is equal to sigma I going from 1 to n delta Wi into Xi. As I said, from geometry you can easily find out what is Xi, X1, X2, etc. You know how to calculate the area of each slice, you know how to calculate W, and you can easily find out what will be the moment due to that. And what will be the resistance mobilized? If I just take, for example, phi is equal to 0, I simply will have only cohesion causing or resisting moment. So I can find out the length of this arc. What will be that equal to? B secant theta I. So the cohesive force, the force along the base is equal to Cu into Li, and the moment due to this force, resisting moment, is equal to Cu Li into R. And if I want the total resisting moment, it's equal to sigma I going from 1 to n Cu Li R. So instead of doing all the trigonometry, etc., by dividing into number of slices, you are finding out each of the slice, and geometry being known, I need to only know the height of the midpoint of the slice and the angle the base of the slice makes with the vertical. And from there I can get, and the factor of safety is equal to resisting moment by moment activating moment, which is sigma I going from 1 to n CUR into Li divided by sigma I going 1 to n delta Wi into, where did we write that, into Xi. So this can be easily done with the hand calculation. You need a graph paper with draw everything to scale. Within about half an hour to 1 hour, you can find out. You should try that in one of the cases. You can take H is equal to maybe say 8 meters, gamma is 18 meters, C is about 25 kPa, and you try. And you will do it for a given circle, then we go around, look around for a number of circles and find out what is the minimum value. This is the principle of method of slices.